we cannot insist that so we have to use that formula for the geometric progression. So it means this one here gives us the moment generating function. Okay, the next example is the Bernoulli distribution. The other time, again, we defined this Bernoulli distribution. We said it is a special case of the binomial distribution, which takes out only two outcomes, 0 and 1. So the moment generating function of a Bernoulli distribution is the expectation of e to power tx. So it is e t p, because where there is x, we have 1, then plus 1 times the 2, and that one is, so this is the moment generating function for the Bernoulli, This is the moment generating function for the Bernoulli distribution. So we just get the e to power t, then x e to power. Actually, here I can. There's a step I missed. I didn't include, but we can see it. So it is. We take the sum e to power tx, then into this is always p. The Bernoulli, we had p to power x, then q to power n minus x. So the n in this case is 2. So when x is 0, then we don't have a p. This will be e of 0, so that one gives us this term. And when x is 1, it will surely give us this term. When x is 1, it will give us this term. When x is 0, we get, so this is the moment generating function for the Bernoulli. Okay, so properties, maybe any question before I go to the properties of moment generating function? Any question?
So in this cell, the cell where you're saying that the G exponential tx.
I'm hearing, please.
Hello.
I'm hearing.
Yes, I'm saying that cell. Where has J gone?
J.
Because you're saying J is in between 1 and n. So in this cell, I only see T up to n.
You see, we are summing from J equal to 1 up to n. Have you seen that?
Yes.
So when you take the sum, when J is 1, you get
I've seen that.
You get E of T. When J is 2, you get
okay.
When J is 3, you get E of 3. And when J is n, you get that. Does that answer your question?
Okay. Then, yes. Then this one, the next one, the Bernoulli.
The Bernoulli.
Of E of n. You're saying it is ETP. So where is this?
Where is it?
Where do you get the?
Okay, I said.
Where do you get this P plus the Q?
The Bernoulli is a discrete distribution. So this is going to be sum from x is 0 up to 1, because it takes on only two values, 0 and 1. So we sum from 0 up to 1. Okay, of etx, then into the function is p to power x, then q to power n minus x, the other one for the binomial. So I said when x is 0, the p to power 0, e of 0 times p to power 0, it gives us 1. Then it will be 1, because the n is 1, so we get 1 minus 0, which is 1. So when x is 0, we get this term here. And when x is 1, definitely this will be 2 to power 0, this will be p to power 1, this will be, so we get this term. So that's where how we reach here. Is that okay? Julian,
okay.
Julian Nanyombi, your hand was up. What are you saying?
Now, you said the process were which one and which one?
Yes, Nanyombi.
Okay, I think I've got what I was asking for, because, okay, my question was, because here they are telling us that J is between 1 up to N. So I wanted to ask, what if I begin from 0, but then that is already answered because
because the range of values is from 1 up to N. Okay, good.
Yes, I've seen it.
Any other question, members? Okay, let me take you to the properties. The properties of moment generating function. Like we saw, the first property is that the moment generating function exists at a point t equal to 0, and that moment generating function at that point, its value is 1. Why do we say this? We know from the definition of moment generating function that it is E expectation. It is expectation of e to power tx. So when t is 0, m of 0 is expectation of e to power 0, but we know e to power 0 is 1. So it is expectation of 1, and since 1 is a constant, expectation of 1 takes us here. So the moment generating function is defined at x equal to 0, and its value is 1. Property number 2, suppose that the moment generating function of x exists in some interval containing 0, then the derivative, this function is also differentiable, so its derivative also exists, and the derivative exists only if it exists in an interval containing 0. So the derivative exists at a point t equal to 0 under suitable conditions, and it is possible to change the order of expectation and differentials. Thus, when we differentiate the moment generating function at t equal to 0, it is the same as differentiating the expectation of etx at t equal to 0. The expectation is a linear operator. We saw that in the previous lecture. So this is expectation of this derivative here. So when we differentiate e of tx, we get x etx here. And when we substitute in t equal to 0, we get expectation of x. So this second property is actually telling us that when we get the first derivative of the moment generating function and we substitute in t equal to 0, we get the first moment. We get the first moment, which is the expectation. So this is how we can use the moment generating function to get expectation. Okay, more generally, if the moment generating function of x exists for all values of t in an interval containing 0, then it is possible to differentiate this any number of times. So it means if we want the second moment, we differentiate the second, we get the second derivative of the moment generating function and evaluate it at t equal to 0. And like we are about to see, if a random variable has an interval which does not contain a 0, then its moment generating function does not exist. The moment generating function only exists for random variables whose outcomes are in an interval containing 0. Okay, so it can also be shown that for a discrete case, when we can differentiate, this is the nth derivative of the moment generating function. It is that, and it is the sum over all values of x, the nth derivative of etx times the probability that, and when we differentiate the nth times, of course, it gives us x. This x is for random variable. It gives us x to power n etx, p of x is x, and when we evaluate the nth derivative of m at 0, then it is the same as substituting a 0 here. This term disappears, so we get x to the power n, p of x. So it is that, and that is e of xn. And clearly, this is called the nth moment of any random variable. This is the nth moment, so it is equal to that. Hence the name moment generating function. Why? Because it generates moments. The first moment, second moment, up to the nth moment, which is that. So I said from this, if I want the first moment, then n is 1, that is expectation of x. I get the first derivative. If I want the second moment, that is expectation of x squared, I get the second derivative, and so on and so forth. And in particular, we have the first moment of 0, it is expectation of x. The second moment, when you differentiate the second time and evaluate at 0, you get expectation of x squared. And of course, from expectation of x and expectation of x, we can use this to compute the variance. All of you remember this formula from the other course we did in year 1, semester 2. So once we have the first and second moment, we have the variance. So the variance can be got from this. Okay, so those are the properties. If you have a question, please, you can raise your hand. Zoom has an option of raise your hand, so I can always see you, or you can unmute and talk. It's okay. I can respond to you, please, on the properties. So next, we want to look at examples. So the first example is already displayed on your screen, so we have a probability distribution function. Let x be a random variable is probability density function, this e to the power negative x, then 0 x. So this is who can tell us what it is? Is it a discrete random variable or a continuous random variable?
Continuous.
Okay, this is continuous. Why? Because it takes on an uncountable domain. So this is a continuous random variable. So we want to find the moment generating function for this. And from definition of moment generating function, it is equal to the expectation of etx. So since the interval is from 0 and onwards, we start from 0 up to infinity. So we integrate from 0 up to infinity of etx, then the function is that. When we evaluate, here the bases are the same, so we subtract the powers and x is a common factor. So we get t minus 1 e of x. And this integral here is finite if and only if t is less than 1. So when we work out this, we are going to generate what we called the geometric series in the previous lecture. And when we substitute, we use the formula for the geometric series, we are able to get the moment generating function as this. But also if you want, you can integrate this. This is easy to integrate. You get 1 over t minus 1, then e of t minus 1x from 0 up to infinity. E of infinity is 0 minus e of 0 when e of 0 is 1. So that's how we get the moment generating function as this. There are so many steps we left out here, which you can always get in your free time. So this one gives us the moment generating function. Now, since the moment generating function is finite on an interval containing 0, you see this was an interval containing 0, so the moment generating function is finite. And so we have gotten the moment generating function, and we can use it to find the expectation, show that the expectation, which is the first moment, is 1, and the expectation of x squared, which is the second moment, is 2. How do we do that? Differentiate here the first time. When you differentiate the first time, you get negative, because this one goes up and becomes to power -1. So -1 into 1 minus into 1 minus t power -2. So it becomes -1 becomes -1 divided by 1 minus t to power minus t to power minus t to power 2. So when you put in t equal to 0, when you evaluate it at t equal to 0, you're able to get 1. And the second question, any question? Questions, please.
So I think you will get 1 over.
Mm-hmm.
Sir,
Mm-hmm.
I'm thinking the differential of it will not be a positive. It will be it won't be a negative. It will be a positive. 1 over 1 minus x squared, just into bracket.
Mm-hmm. X squared into bracket. It won't be okay.
No, it will be 1 over,
Mm-hmm.
open the bracket, 1 minus t squared.
Mm. It will be, you take it up, it is 1 minus t per -1. So differentiate, you get, oh, there is a derivative inside. You multiply by the derivative inside.
Yes.
Okay, so that's
Yes.
okay. So can we go to the next example, please? Next example, we want to look at a continuous random variable still, which is the uniform distribution.
Excuse me, sir.
Yes, please.
Why are we saying that the second moment will be 2?
We differentiate this function the second time and then substitute in 0. We should be able to get 2. You will verify that.
Okay.
Okay, so we are here. This is the uniform distribution or the rectangular distribution. Now, its moment generating function is e of tx, which is integral from a up to b of e of tx. So we can put constants. Okay, when we integrate, this is what we get. Then from a up to b, it gives us this. But the moment generating function only exists in an interval containing 0. So this one cannot give us the moment generating function. Why? Because this interval does not contain a 0. Therefore, it is not possible to find the mean and variance using the moments because this interval does not contain 0. Okay, so there is a theorem. This theorem is the linearity of the moment generating function. The MGT is the moment generating function. So this theorem says if I have, okay, time is almost going. I have 9 minutes. It's okay. In 9 minutes, we'll be done. We'll be able to end this lecture. Okay, let x be a random variable whose moment generating function is this. If y is another random variable defined in terms of x, then the moment generating function of y is e to the power bt, then times moment generating function of at. And the proof for that theorem is simple because from definition of moment generating function, the moment generating function of random variable y is e to the power ty. So this is e. What is y? Where there is y, we put ax plus b, and this is e. This is e to the power tax plus e to the power bt. But bt is a constant since it is independent of x, and from properties of expectation we can pull out the constant, so we get this, and we see that where we have atx, then it is the moment generating function of that. So it means that This function we are looking at, that we are calling the moment generating function, it is a linear operator. In other words, applying it on the sum is this, okay, the moment generating function of the sum is the sum of the moment generating functions of each of the terms. Okay, next we look at another theorem, the uniqueness of the moment generating function. If x and y are two random variables with identical moment generating functions, then for all values of t in the interval containing 0, the distribution of y and x must be identical. So this theorem is telling us that two functions, two random variables cannot have different values of moment generating functions. If the random variables are the same, if the moment generating functions are the same, then it means that even the variables are the same. In other words, a random variable x can have a unique moment generating function. You can't find two different generating functions for the same random variable x. So this theorem is useful in identifying distributions of a given random variable. Once we have the moment generating function, then we can easily identify the distribution, whether it is binomial, whether it is geometric, whether it is Poisson, and so on and so forth. Okay, so that is the uniqueness theorem. And then there's an exercise, and then we end the lecture. Any question? Questions, questions, questions. Questions, questions, questions. Questions?
Excuse me, sir.
Yes, please.
Why don't you do for us that part? Okay, one of those.
Which
Anyway,
part?
for example, you do for us part A.
Part A. Okay, part A is surely easy. I can do it only that, okay, I do part A. Let me try to work out part A. But then you have to give me some time because I have to write on paper. I have to write on paper and then take a picture. Okay, let me work out part A. Let me work out part A. As Madame Manuel has suggested. So part A, we have t of x is equal to a half. X is taking on -1, 0, and 1. So the moment generating function of that is by definition expectation of e tx. So this part A, I can see it is a discrete random variable. Why? Because it is taking on specific values. So the expectation is going to be taking the sum from x is -1 up to 1 of e tx, then times a half, because a half is its random variable. So this will give me a half is a constant. Then I take the sum. When x is -1, I get e power -t, plus when x is 0, I get 1, because e of 0 is 1, plus when x is 1, I get e of tx. So this will give me a half into 1 plus e negative t plus e t of x. So when I open brackets, I get a half plus a half e tx, then plus a half E negative tx. So this one here alone is the moment generating function of 1, and that's what we have been asked. But also, if I want to get the first moment, for example, I can differentiate here with respect to t. So when I differentiate, I get with respect to t, I mean with respect to x, this will be t times a half e t. No, differentiate with respect to t, not with respect to x. So this one will be a constant, so I get a half, then x e of tx, then this is x, okay, x is I need to admit this one, okay. When x is, no, I have t's only, I don't have x's, sorry. This is just a t, there's no x here because I'm putting the value of x as 1. So this x is not there, so it's like that. So when I differentiate, I get with respect to t, this one is half e of t minus a half e of negative t. This is the first derivative. Then when I get the first derivative at t equal to 0, when t equal to 0, this gives me a half minus a half actually. So this is equal to 0. So it means expectation of this for this random variable is equal to 0. Okay, let me scan my solution and then I put it on the computer and I share with you. But I have 1 minute. I don't know. I have 1 minute. I don't know whether I need to schedule another session. Or let me see if I can show you my camera. Let me put my like this. Are you able to see my paper?
Not at all.
We can't
Not at all.
No, sir, we are not seeing anything.
You can put it on WhatsApp.
You put it on WhatsApp.
Maybe you can put it on WhatsApp and we can share it.
Okay, I'm going to scan and share and put it on WhatsApp.
Okay.
Okay, so there's an exercise for you there. We end the lecture here. Have the best of the weekend.
Okay.
Mr.